Hi everyone, in this recording we will be going over section 4.2 area. So now we'll be going over sigma notation. So this symbol right here is uppercase sigma, or also known as a summation. So the sum of n terms, a1, a2, a3 up until an, is written as I is equal to 1, where I is the index of summation, and n is the total amount of terms that you're adding up, and ai is the term. So we will have a1, our first term, plus a2 plus a3, all the way up until an, our last term. So ai is the ith term of the sum, and the upper and lower bounds of the summation are n and 1. We have some examples of sigma notation. So we are taking the sum of I from I is equal to 1 up until 6. So our first term, I, will be equal to 1. The second one, I is equal to 2. The third, I is equal to 3 up until 6. So the sum, 1 plus 2 plus 3 plus 4 plus 5 plus 6 is equal to 21. For this example, we are starting now from I is equal to 0 and up until I is equal to 5. So the first term, we will plug in 0, so 0 plus 1 is equal to 1. The second term, we'll plug in a 1 right here, so 1 plus 1 is equal to 2. The third term will be 2 plus 1, which is equal to 3. The fourth term will be 3 plus 1, which is equal to 4. The fifth term will be 4 plus 1, which is equal to 5. And then the last term, our fifth term, 5. So we'll plug in 5 plus 1, which is equal to 6. So summing those gives us 21. Now we are starting off from I is equal to 3, and we are summing I squared up until 7. So the first term, 3 squared, second term, 4 squared, third term, 5 squared, fourth term is 6 squared, and the fifth term is 7 squared. So summing all those gives us 135. And then lastly, we are starting from I is equal to 1 up until 5, and we are summing 1 divided by the square root of I. So for our first term, we plug in 1, the second term we plug in 2, third term 3, and so on, and we sum all of them. So 1 over the square root of 1 plus 1 over the square root of 2 plus 1 over the square root of 3 plus 1 over the square root of 4 plus 1 over the square root of 5. So now we will be going over general rules for the summations. So for the first one, if we have the sum from I is equal to 1 up until n of a constant c, then that will be equal to c times n. And we have the proof right here. Since we are adding c n many times, that is the definition of multiplication. So we're just doing c times n. And then we have these 3 other rules. The second one is the sum from I is equal to 1 up until n of I, that will be equal to n times n plus 1 divided by 2. This third rule, we have the sum from I is equal to 1 up until n of I squared will be equal to n times n plus 1 times 2n plus 1, all divided by 6. And then lastly, we have the sum from I is equal to 1 up until n of I cubed is equal to n squared times n plus 1 squared, all divided by 4. Now here's the proof of the sum of I is equal to 1 up until n of I. And it looks like a lot, but I just rewrote some of the stuff just so it'd be easier to visualize. So first we just write carrying out the sum on the right hand side. We have 1 plus 2 plus 3 up until the largest term, n. So we are summing all these terms. So now we can do 2 times the sum of I from I is equal to 1 up until n. So we can let this portion, the summation of I, be equal to s, our sum, and we just carry out the sum right here. Now the second sum will be the same thing but written in the opposite direction. So we will start with the largest term, then the second largest, third largest, up until the smallest term, 1. So right here, we're just doing 2 times s because we are adding them. So we are adding the first sum, 1 up until the largest term, and the second sum, the largest term, up until the smallest term. So now we can carry out the addition. So we have 2s, so we're just adding the sums, and we will add vertically. So 1 plus n is n plus 1, 2 plus n minus 1 is n plus 1, and 3 plus n minus 2 is n plus 1. Now we keep on doing that up until our last term, so n plus 1 is equal to n plus 1. So now we see on this right hand side, we are summing n plus 1 n many times. So this is what this line means right here. We have n times n plus 1. And on the left hand side, we had 2s. So 2s is equal to n times n plus 1. Now solving for our s, or our summation right here, we can divide by 2 on both sides. So that means s is equal to n times n plus 1 divided by 2. Or right here, in our final form, we have the summation from I is equal to 1 up until n of I is equal to n times n plus 1 divided by 2. Now we are going over the proof for the sum of I squared from I is equal to 1 up until n. So we will be using this identity, I plus 1 cubed minus I cubed. Later on, we'll see that the power, the cube, will cancel out and we'll be left with a degree of 2. So once we expand this, we will get 3i squared plus 3i plus 1, but that is getting ahead. So first, after using this identity, we can split this sum into 2 different sums, and we will be subtracting because right here we are subtracting. So we will have the sum of I plus 1 cubed from I is equal to 1 up until n minus the sum of I cubed from I is equal to 1 up until n. So now we can carry out these 2 sums. So this first sum, we have 2 cubed plus 3 cubed up until our largest term, n plus 1 cubed. Now this second sum will be 1 cubed plus 2 cubed up until our largest term, n cubed. And plus n cubed, sorry. And then we are subtracting. So we will see that the intermediate terms will cancel out, and we are left with the boundaries. So we'll have 2 cubed minus 2 cubed, that will cancel out. 3 cubed minus the 3 cubed, that will be here. And then up until n cubed minus n cubed. Lastly, we will be left with n plus 1 cubed minus 1 cubed, which is just n plus 1 cubed minus 1. So now we can set this sum equal to what I said earlier, the expanded form of this. So it'll be the sum of 3i squared plus 3i plus 1. Now we can take each of these sums individually, so we will have 3 times the sum of I squared from I is equal to 1 up until n, plus 3 times the sum from, the sum of I from I is equal to 1 up until n, plus the sum of 1 from I is equal to 1 up until n. Now these 2 sums, we already know the answers. The sum of a constant from I is equal to 1 up until n will just be n times that constant. So n times 1 will be the third sum. The second sum, we know that this sum, I from I is equal to 1 up until n, is n times n plus 1 divided by 2, and then we need to multiply by 3, and then we can just carry this first sum down. Now we can carry all these 3 terms that we just wrote, or that we just found, down, and we can set that equal to these terms that we found earlier, first when we expanded this identity. So now we will have 3 times the sum of I squared from I is equal to 1 up until n, plus 3 times n plus 1 divided by 2 plus n is equal to n plus 1 cubed minus 1. Now we can isolate the summation from I is equal to 1 up until n of I squared, and that'll leave us with n times n plus 1 times 2n plus 1 divided by 6, after combining like terms and everything. So now the remaining proof is similar, and you're encouraged to try it for the last summation. Now we are going to evaluate the sum I is equal to 1 up until n of I plus 1 divided by n squared. So first we can take out the 1 over n squared, since we are working with I, we are summing the I. So taking that out, we have 1 divided by n squared times the sum from I is equal to 1 up until n of I plus 1. Now we can break this into 2 sums, so we'll have the sum from I is equal to 1 up until n of I, and the sum from I is equal to 1 up until n of 1. Now this is a constant, so using our first rule that we had stated previously, that would be c times n. So in our case, c is 1, so then the sum, this one, will be 1 times n, so that is n. And then we also have a general rule for this summation, so from I is equal to 1 up until n of I, that is equivalent to n times n plus 1 divided by 2. And then now we can distribute the 1 over n squared that we had taken out to both of these terms, and we can add them, and that gives us n plus 3 divided by 2n. Now we can take the limit as n approaches infinity, and that will be equal to 1/2. So now we can use the 5 rectangles to approximate the area under the curve for the function f of x is equal to negative x squared plus 5 above the x-axis and bounded by x is equal to 0 and x is equal to 2. So we have 5 rectangles, and we can use the right endpoints of the rectangles and those will be given by 2i divided by 5. So this endpoint right here for the first rectangle will be 2 times 1 divided by 5. This second endpoint will be 2 times 2 divided by 5, and so on. And we see that the width of each of these rectangles will be 2 divided by 5. So the sum of the areas of the 5 rectangles can be denoted by S lower, and we're taking the sum from I is equal to 1 up until 5 because we have 5 rectangles. And the area of a rectangle is given by length times width. So we said the width was 2 over 5. And for the length, we can evaluate our function at the endpoints, at each of the endpoints. So for the first endpoint, we have 2i over 5. So we will evaluate f of 2i over 5, which is 2 times 1 over 5. So we can plug that in for x. And then that'll be our length. So we multiply the length times the width for the first rectangle. And we do that for all 5. So we can denote that as our sum from I is equal to 1 up until 5 of each of the lengths, the respective lengths for I, times the width. So once we carry that out, we will get that the sum of the areas is approximately 6.48. And then this figure 1 shows the lower sum for the area under the curve for our function f of x. Now we will be taking the upper sum. So we see that the rectangles go above the curve, whereas before when we were taking the lower sum, they went below the curve. So right here we had an under approximation, and we will see that we will get an over approximation. So for the upper sum, we will be using the left endpoints, these left endpoints, and they will be given by 2 divided by 5 times I minus 1. And so the width of each of these rectangles will still be 2 over 5. So the sum of the areas of the 5 rectangles, now this time it'll be S upper. So this should be upper right here. Once again, that'll be the sum from I is equal to 1 up until 5, because we have 5 rectangles, and we are doing length times width. So the length of the first rectangle, we will just evaluate our function at 2 over 5 times 1 minus 1, because we're plugging in a 1 for our first term. So that'll be 0. So we'll evaluate our function at 0, and that is positive 5. So that means the length of this first rectangle will be 5, and our width is 2 over 5. So 5 times 2 over 5 is 2. So that means that the area of this first rectangle is 2. Now we repeat the process for the other 4 rectangles, and we take the summation of all 5 areas. And that'll be approximately 8.08. So we notice that the true value of the area is between the obtained values from the lower and upper sums. So for the lower we had about 6.48, and then the true area will be between 6.48 and 8.08, the area we got from the upper sums. So it seems like these approximations would be better if we increased the number of rectangles. We'll be going over finding the area by the limit definition. So we let f be a continuous function on the closed interval ab. First, since we plan to divide the interval ab into n subintervals of equal width, the width of each subinterval must be, so we let delta x be equal to b minus a divided by n. Now, since f is continuous, the extreme value theorem guarantees the existence of a minimum and a maximum value of f in each subinterval. So f of lowercase mi will be the minimum value of f on the ith subinterval, and f of uppercase mi will be the maximum value of f on the ith subinterval. We can now define 2 sums, one that uses the minimum values of each of the intervals and another that uses their maximum values. So the first sum will be our lower sum, and that will be denoted by lowercase s of n, and that will be equal to the sum from I is equal to 1 up until n of the minimum value of f on the ith subinterval, so this f of lowercase mi, times our delta x. Then we will also have our upper sum, which will be denoted by uppercase s of n, and that'll be equal to the sum from I is equal to 1 up until n of our maximum value of f on the ith subinterval, so this f of uppercase mi, times our delta x. So we know that the true area is between, so it'll be less than or equal to the upper sum, and greater than or equal to our lower sum. The upper and lower sums for the function f of x is equal to x squared, above the x-axis bounded by x is equal to 0 and x is equal to 2. So we see that the lower sum we will be using the left endpoints for this part A. We see that for the lower sum we have an under approximation, and then for the upper sum we will be using the right endpoints, and this is an over approximation. So we have delta x is equal to b minus a over n. In our case, our b is 2, and our a is 0, and 2 minus 0 is 2 divided by n. So that means that the lower sum points, the left, are going to be denoted by lowercase mi, and that will be equal to 2 times I minus 1 divided by n. And the upper sum points, the right hand side, will be capitalized mi, and that will be equal to 2i divided by n. So for the lower sum, lowercase s of n, that will be equal to the sum from I is equal to 1 up until n of f of lowercase mi times 2 over n. Now for the upper sum, it will be capital S of n, and we will be taking the sum from I is equal to 1 up until n of f of capital Mi multiplied by 2 divided by n. We will be evaluating these sums. So for the f of mi, we just plug in our mi into our function. So our function was x squared, and mi, lowercase mi, was 2 times I minus 1 divided by n. So this is what we have right here. And we are squaring that because our function is x squared. And then that was the length. Now our width was 2 divided by n, and we're summing from I is equal to 1 up until n. So we can take out the n terms, since those are independent of the sum. We are summing from I is equal to 1 up until n. So then we can take out the n terms as well as the constant 8, and then carry out expanding these and multiplying by the 2, and we get that we are taking the sum from I is equal to 1 up until n of I squared minus 2i plus 1, and that will be multiplied by 8 divided by n cubed. So once we evaluate this sum and multiply the 8 over n cubed, we get that the lower sum is 8 divided by 3 minus 4 divided by n plus 4 divided by 3n squared. Now we repeat the process for the upper sum. So now we are evaluating our function at uppercase mi, which was 2i divided by n. So we are plugging in 2i divided by n into our function f of x is equal to x squared. So we will be squaring the 2i over n and multiplying that by 2n. So once again, we can take out the 8 over n cubed, because that is independent of the sum, and then we will be summing from I is equal to 1 up until n of I squared. Now, upon evaluating this and multiplying back the 8 divided by n cubed, we get that the upper sum is equal to 8 over 3 plus 4 over n plus 4 divided by 3n squared. So to get those sums, we just use the previously developed sum formulas. So as expected, the lower sum, 8 divided by 3 minus 4 over n plus 4 divided by 3n squared, is less than our upper sum, 8 divided by 3 plus 4 over n plus 4 divided by 3n squared. So we notice that as we take the limit of n as it goes to infinity, of both the lower and the upper sum, they both go to 8 over 3. So the limit of both sums approached the same value. So this is no coincidence. Now we have a theorem that goes over what we just saw. So we let a function f be continuous and non-negative on the closed interval a to b. The limits as n approach infinity of both the lower and upper sums exist, and they are equal to each other. So that is, if we take the limit as n approaches infinity of our lower sum, that will be equal to if we take the limit as n approaches infinity of our upper sum right here. So here delta x is equal to b minus a divided by n, and f of lowercase mi and f of uppercase mi are the minimum and maximum values of f on the ith subinterval. So this result follows immediately from the squeeze theorem. So from the previous theorem, we can conclude that the choice of points in the ith interval is irrelevant to the value of the sum. So we can do the following. Now we provide a definition for the area of a region in a plane. So we let a function f be continuous and non-negative on the interval, in this case the closed interval from a to b. The area of the region bounded by the graph of f and the x-axis and the vertical lines x is equal to a and x is equal to b is given by, so we take the limit as n approaches infinity of the sum from I is equal to 1 up until n of our function evaluated at the point ci times our delta x. So here ci, that value that we are evaluating our function, will be between xi minus 1 and xi, and our delta x will be equal to b minus a divided by n. Now we will be approximating the area using the midpoint rule. So the midpoint rule is the choice of points, ci, where that is equal to our second point minus our first point divided by 2. So the midpoint between these two points. So we'll use it to approximate the area of our function f of x is equal to sine of x in the closed interval 0 to pi, with n equal to 15. So first, delta x will be equal to pi over 15, because our b is pi, our a is 0, so pi minus 0 is equal to pi, and n is 15. So pi over 15 for our delta x. The midpoints of the rectangles are given by 2i minus 1 divided by 30 times pi. So the sum of the areas of the 15 rectangles, once again, we evaluate our function at our ci, so right here, for each I, from I is equal to 1 up until 15. So that'll be our length, and then our width will be pi over 15. So carrying out this sum gives us approximately 2.00366. So here's the figure for our function and the midpoint sum for the area under the curve f of x.